正在录制此会议。
Okay, so good morning everyone. Hope you enjoy the video this week and sounds maybe the few times I record the video myself, so not sure. We'll see. I just speak with my camera and there will be no other response. Okay. So anyway, so I will keep on talking about our lecture, especially in lecture 9. It is the first step of our logic circuit and the CMOS device. Okay. So this time we talk about the chapter 8, which is to connect the metal oxide and semiconductor. So just to recap what we already covered before, we have the BJT, which we can control the current using forward reverse biasing. And the data we connect with the BJT, the metal connection. And for the metal connection, we need to consider what is the terminal or what is the corresponding carrier. So there will be metal to semiconductor connector. And then next time we talk about the metal oxide semiconductor in which we insert additional insulating layer. That means you can control the carrier without any current. Okay, so there will be something which is interesting. Would that be possible to apply both BJT and the metal oxide semiconductor device to the transistor? Okay, so it is the invention of a really efficient logic circuit, especially so we can control the current without the additional data or additional current. Okay, so the idea here is we will propose, especially you heard about like really advanced technology, inventing the nanometer, even 1 nanometer technology. They consider what is the device they prefer to work out is typically logic transistor device. And for those logic transistor device, they are talking about CMOS, or this is the MOSFET. So for the MOSFET structure, they are structure briefly produce the circuit or is the device architecture. So the idea is first, we still have like a PN, GNP or NPN junction, like the BJT connection. But instead of just using street metal to connect different areas, we want to have the metal oxide between the independent device. So here is the really simple architecture, but I think you can draw a really nice picture. This one I started maybe 5 years ago, but you can draw it using ChatGPT Gemini, using a really fancy configuration. But the idea is that, okay, so we already talked about the BJT, so that means we get like an NPN connection or PFP connection. And here we still use this connection. So typically you get like the N plus P type, N plus type. So we typically call it is the source and drain. Unlike that, we call in BJT, we have the emitter, collector, and the base in the middle, right? And then here is we use different we use different symbol to label the combinations of these MOSFET. So for this examples, we have the substrate as the P-type semiconductor, and then it comes we have the high doping along source and the third side. And then it comes if you are working with the conventional BJT system, we just connect with the metal at 3 different terminals. But for this one, instead of using 3 metal connection, we get extra isolation layer or into the data layer in between the panel. Okay, and then we connect the metal. So you can see this skin in between the channel, in between the solder area. It is what we in the previous lecture, in the previous online post, we talked about metal oxide semiconductor. What is the carrier permeable and the accumulation voltage and the depletion region on the different biopsy. So if you are able to connect with two sides, you are able to tell how much actual carrier accumulating with this semiconductor layer, and then what is the corresponding service potential. Okay, so this time we talk about the service potential, which is related to the biosing and the metal part, and also what is the corresponding carrier accumulation along the surface, right? So we need to first deplete the majority carrier. In this example, what is the majority carrier? We have the substrate which is p-doped. The p-doped system gives you like the whole of the majority carrier. So if you apply the biopsy, you need to first deplete the whole area. And then if you want to accumulate the majority carrier, you need to use electron. Okay. So what happened here? The idea is that okay, so we take metal oxide semiconductor field effect transistor. So we abbreviate as MOSFET. So for this MOSFET, why we turn this one is because we have the scheme in which the scale architecture is metal oxide semiconductor. So it is the feature of this field device. Okay. And how we call the field effect transistor? Because we apply voltage. If there's a voltage, you divide it by the distance, you get the electric field. And then you have electric field. We change the carrier, we change the surface potential. And the data is once you have different carrier, maybe you can conduct the current, just like the BJT. Okay. So remember starting the BJT consideration, we change the current, we change the biasing condition using forward biasing, reverse biasing. And then once you conduct the current, typically you get a depletion region change, and so you change the field, electric field. So in this case, we just use metal oxide semiconductor and work as a field in dependent transistor in order to control current. Okay, so that is the meaning of the MOSFET metal oxide semiconductor field effect transistor. Okay, that's also the reason I think back to maybe 15 years ago, people work with the MOSFET already, with the planar MOSFET, but now they are still working as really same architecture. But in change, how do we couple with instead of your planar transistor can go up with the vertical transistor or gate-all-around. Okay, but we have not yet talked about further fancy architecture like a sleep-based complementary field effect transistor or other like a nano carbon tube or other really novel device. Okay, they are still under research. So the reasons we want to use these devices because it is in the design of the logic, especially for integrated circuit. Okay, and for these schemes, they have two advantages. The first one, of course, it is simple. The other one is really small. Okay, so for all of these architectures, you can downsize it would be several tens nanometer if possible. But in most of the regular case, I think back to my age, you can start with the transistor with like a few tens or even hundred micrometer. Okay, it should work depending on how much current you prefer to conduct. Yes. So for this kind of device, people typically talk about the very large semiconductor integrated circuit design, VLSI. So you get a very large scale integrated digital circuit. So you can connect with different digital circuits together. Also, we didn't talk about what is digital circuit and uh, what is the purpose for that. But if you are interested, you can go back to undergrad study. There will be some explanations why we want to use logic circuits. That will give you more simpler case, especially understands why these tiny devices can make things really different. Okay. Now that is the power. So we can build up this structure into brilliant device, all within the really small chip. Okay, so that is the power of this transistor or MOSFET. Okay, so we talk about this later, and we want to show you how we operate this device, especially how do we conduct the current, how do we conduct with different multi-carriers. So here's the idea. So we already talked about our simple case in the previous lectures. We have the gate outside semiconductor. So previously we just get rid of the social side. That means we only have the connection in between. So if you have the connection in between, if you apply positive charge for the p-type semiconductor, what happens here is that if you have the forward bias, you build up the electric field from the metal part to the semiconductor part. So that's what happens before. So you can draw the Venn diagram to build the Fermi level, and then you accumulate a partial electron layer along the surface of outside, right? So once we have this one, how much voltage or surface potential we need to provide? We need to first deplete the majority carrier, right? And also we want to get a 258. What is fire in the previous slide? I hope you already see the video, right? Because it has already been 1 week. So the fire means that of the difference potential between the Fermi level and the intrinsic level. Okay, so you need to first apply the voltage to deplete the majority carrier. That means you kill the Fermi level the same level to the intrinsic level. So that means after this potential, you get exactly like a really low doping concentration inside the semiconductor. So for silicon, for instance, again, remind you the intrinsic level is typically 1.5 times 10 to 10. That means the doping concentration is low. If you divide it, the density of the semiconductor, silicon density, it will be over 5 times 10 to 22. So that means you only have 10 to minus 10, 10 to minus 10 probability that the ionized atom, ionized majority carrier inside this substrate. Okay. But later on, if you further increase the voltage along the metal part, what happens here is that you get a stronger field. You get the stronger field, you get a possibility to accumulate additional magnetic carrier along the surface. That means we get an electron. And as we explained this week, why we have this majority electron, where it come from? You have several ways, like previously we studied it is coming from the long distance of this magnetic field. So previously we mentioned, for instance, that here is the metal, here is the oxide, and then here is the semiconductor. So last week we talked about if you apply the potential, it is possible to accumulate a certain carrier at a negative carrier as the electron field. But where is the electron come from? Because it's multi-carrier, so you need to strip the electron from far away distance. And that means you get a really slow response, right? That's what we talked about. If you modulate the distance and see what is the capacitance, and this capacitance will be voltage dependent. That means if you get a strongly accumulate volt, that means you get a certain capacity, but this capacitance will go down because there is no majority carrier. And then later on, if your speed is slow, you can recover it because you get attract this multi carrier from other distance. As long as the speed is within like one K or less than 100 kilohertz, it's really slow. But if you modulate it with fast, the carrier cannot respond with fast. So this accumulation channel seems to be disappeared. Okay. So on the last constant, what you actually modulated with is the depletion region of this scheme. Okay. So when you modulate this scheme, that means you divide it by what is the capacity? Epsilon multiplied with area divided by the distance between two charge sheets. Okay. So if you get a depletion region like we previously used reverse files to get a depletion region, deplete the majority carrier out of this region. If you get a large reverse voltage, you get a large depletion region. That means your present turn is done. So what you get is that if you get a voltage into the accumulation layer, but the response is really fast, you cannot catch up the skin, so the capacity will go down. Okay, so that's what the figures we showed. So we talked about two different frequency response. One scheme in reverse bound, you get this accumulation, and this scheme can catch up the modulations of your capacity. So you get up because you get a free layer or the accumulation layer of the multi-carrier along the surface of semiconductor. Then you recover the capacity. But at that times, if you use really high speed to modulate the schemes, you deplete the region, and then the depletion region will be expanded further or get a wider depleted region. That means actually your capacity goes down. That means you get a certain scheme showing different modulated frequency. What is the capacity work here? Okay, so think about it is just like a really central part of this semiconductor device. So let's consider if you are working with additional source and drain, in which we build up an additional two domain. One good thing is that instead of drawing the minority carrier from a really far away distance, what happens here is that, okay, so since we have a really high doping, we label it as N plus N plus. That means we get N-type doping. So what happens here is you doing a same reverse biasing. You deplete the majority whole carrier first from the P-type semiconductor, and then using high level voltage to accumulate the multi-carrier. What happens here is that the coming source for the multi-carrier, it can come in from these two types, okay? Because it's a type system, and maybe it's boundary is far away, and the multi-carrier means that you get a really least concentration, but there will be a really large hole or a large pool for you to attract the multi-carrier. So this may be really simple. I'm not sure if I can give you a right example, like you are trying to eat some drink beverage, for instance. I'm not sure you've seen the straw strap, and then you try to draw at a different point, and if you draw strongly, it appears will first coming from the the area in which we get higher electron concentration. So that will give you a chance to easily attract the electrons along the semiconductor surface. That means the response should be higher or faster than the metal oxide semiconductor phase. Okay. So you are able to get a higher response in comparing with just the metal semiconductor oxide semiconductor. Okay. And then once typically we design, it is that okay, so first we talk about the voltage applies to the gate. Okay. So if you just get the gate without voltage, you apply with nothing, you get 0 volt. What happens there is that the semiconductor is pretty isolated, just like PN junction. Okay. So you consider a PN junction, if you connect the PN junction without the internal biasing, what happens there? There's a depletion region, and there will be no current flow. Because first, there's no external biasing. The second thing is that there's a boundary between the PN junction. Even for P-type semiconductor and the N-type semiconductor, they both have majority carrier. They are conductive. But once you connect with each polarity, get nothing because there's a potential in between to forbid the current flow. Okay, so even if we just have a really low voltage like 0.2 or 0.3 volts, you cannot conduct the PN junction. But here we do the same thing. If you get the source and drain, we consider it should be like a source, like we suppose the charge, and then the drain means that we draw the charge. That will be a simple text, 2-point text. So what happens here is you get a small voltage across source drain. What happens here? If there is no driving gate voltage, if there is no gate voltage, you can think that what is in the middle of the channel? It is P-type semiconductor. And along the source and drain, it should be like the N-type system. So there will be a potential between the PN junction. You can consider there are two PN junctions separately. So even if we apply a small voltage across source and drain, even both the source and drain are highly doping, you get a conductive bulk material along source and drain. There should be no current because in the middle of this PN junction, in the middle of this junction hole, you get a P-type semiconductor. So even if you get the free electron, a lot of free electron in source and drain, once it touch the PN junction region and touch the P-type region, that will be the multiplier. So you get no current flowing through the source drain, even there's a really small voltage effect. And for the MOSFET, unlike the PN junction, for PN junction, if you get a really high voltage, that's possible to turn on the PN junction. If you are using the forward biasing, like about 0.6, 0.7 volt, You get current flow because there is no potential. The depletion region shrink, and then you get the current flowing through the P-N junction. And here is for the social junction, you can think kilometer as long as you didn't break it. As long as the voltage didn't break the device. You always build up a potential in between because you can think even we apply forward biasing, but once you get forward biasing, that will be something like okay, so there is no depletion in between. But how about the other side? Okay, so for instance, if you want to apply a really high voltage from here to here, and then what is the biasing condition? If the potential in P-type region is higher than N-type region, maybe it's forward bias, right? But if you get a higher potential straight layer, that means you get a reverse biasing along N-type to P-type region. So even if you apply really high voltage here, only one region can give you forward biasing, for the other one it will be thin. Okay, so that means what happened here? You get nothing. Okay, that's the typically condition. But sometimes you may consider if you get a really high voltage, one is forwarding, the other one is deplete. The depleted one seems to work a sweeping condition, just like the BJT. Okay, that could be possible. But what is the request? What is the request condition for BJT? The length of these two poles should be really small in comparing with the decay of your multi-carrier, decay length of the multi-carrier. That means it should be like at least 10 micrometer or 5 micrometer, something like that. Okay, it could happen for the really advanced MOSFET because for the advanced MOSFET, the channel length is really small or even down to a few tens of millimeter. Okay, so for all of these things, that if you get applied a really strong biasing, what we previously saw that you can use the central pole to control the current. That's what happens for BJT, right? Because you can use the control gate to reverse biasing from both sides. And then for most cases, that is the scheme the scheme is different. The scheme is that how do we build up the channel? As long as we have the channel, we can conduct the current. So the idea for this one is that, as we mentioned for the multi-carrier, if you can accumulate this multi-carrier, even if we can just apply 0.2, 0.1 volt, there will be a channel because we have n-type electron, n-type as a channel, as a electron channel for the current to pass through. Okay. On the other side, if you are working with different MOSFET, this one we have the MOSFET in which the conducting channel is n-type, is electron. If you are working with another one, for instance, if you use the n-type substrate and you dope the source and drain with P+, which is hole, and you have really high density or high concentration in the whole carrier. And then for the channel one, you need to use the reverse biasing to accumulate the channel or the hole along the surface, and then you can conduct the current using hole. Okay, so that will be some place we need to think about. So typically you have 4 different points for both main. Instead of using just the source drain as the 2-point connection, we have the gate control. And for this gate control, it typically has different voltage on the body. The body means that what is the grounded substrate, what is the substrate potential. Okay. The reason is because in the previous lectures we talked about metal oxide semiconductor. We connect the metal to semiconductor with certain biasing potential. Okay. And for semiconductor part, there will be a reference potential. That means how much potential difference between metal and the semiconductor. So you need to consider first under that scheme, what is the voltage between the metal to semiconductor, and what is the voltage along the channel. That will be four-pole system. It will be a little bit complicated, but not so much if you separate this issue. The first one, the 2-pole, is introduced by metal oxide semiconductor. The second one is like the channel. How do we conduct the current using this multi-carrier? Okay. And once you have this multi-carrier, let's go some math, some pretty complicated form. So for this one, maybe I want to give you some detailed introductions here. So traditionally, if you told for this one, the size is small and then the process is simple, it would be like a pretty similar process considered for the software system. And then typically we want to first design some scheme, like a parameter we want to do. So the first one is that we take the n plus or n most distant most state as an example. Typically we have the outside and the maple on top of it. And under the schemes, the most important parameter we set here is the length of the channel. So what is the distance between here? Okay, that is important as I previously mentioned in most of the technology, the length define the technology node. Okay, so before like 16 nanometer technology, CMOS technology, maybe people with the 0.13, in which we get 113 nanometer. And then later on it became like 65. It became like what else? I kind of forget what is the order. And typically it will be increased by 1.6. Okay, so I think maybe you are mostly familiar with TSMC. So if you go back to TSMC technology, I think 10 years ago, for instance, the mature system or the advanced technology is around 10 nanometer. And the later it became 7 nanometer, and the later it became 5 nanometer. Why we use this order? So why we do not say this 10 nanometer to 9 nanometer or to 8 nanometer? The reason is more slow. So based on most of what is the procedure? Every 18 months, we double the density of your transistor. So if you want to double the transistor, that means your side length should be shrinked by 1.6. 1.6 by 1.6 is around 2. Okay. So if you want to double the density, you want to shrink the size, the edge of your chip. Okay. So once you shrink the dimension of the length, that means you shrink the entire transistor by 1.6. So if you divide the 10 by 1.6, it gives you like the 7. 7 divided by 1.6, it gives you like a 5 nanometer. But actually, it is not physical dimension anymore. So as previously we have already mentioned. So what has happened here is that if you go back to the previous technology node, so what should I say? Maybe here is a year, and then here is the technology node. And then here, and you see the color. Here's the physical dimension, physical channel length, L. Okay, so previously, if you work with the dimension about like 20 nanometer, the dimension go together with the technology. Okay, they are pretty similar. For instance, if you get like 6.5, then what is next technology divided by 1.6? How much is it? 48. I'm not in that technology here, so I'm not familiar with that. I know the previous one, I think there will be additional to like 0.18, 0.13. It's 130 nanometer, and the later on you have, I kind of forget anyway. So you can trace it down. But the later on, so once you go down to around 14, I think it's 24 in TSMC or 22 in TSMC. So it is split. So for instance, it is 24, 20, or 24. I kind of forget it to check online and then see what is the transfer. And what happened here is that the physical dimension will be still the same. And for the current technology in TSMC, for example, 2 nanometer or 3 nanometer, around this year, and then we check. Sorry, I use different color. Wrong color. The white one will keep on going down because they want to still still use the CPU, GPU, so they want to earn more money. So they claim that it is 3 nanometer technology or 2 nanometer technology. That's what is we working on right now. And I think that, in their research and development, they are working with like 1.8. I think 18A. It is from Intel, right? It's close to what the people work in TSMC 1.8 nanometer, or they also call it the 16N. Okay, so they keep going down. What happened for physical channel? They are saturated something like this. Okay, so corresponding to well, there's I work with 7 to 5 to 2. I work these 3 areas. And then the physical channel length, the corresponding is like a 14 nanometer, 12 nanometer, the 10 nanometer. Okay, so the channel length didn't change that much because it is saturated. But why people always claim the technology goes down, like we get 2 nanometer, 1 nanometer, because they can raise the price? Maybe, yes. But they still boost the performance of your MOSFET by different way. Okay. So we previously defined what is the most what is the advantage of this technology because you shift the dimension of your chip, you boost the response, maybe not the frequency but the current, how fast you charge and deplete the current. Okay. So they use different way. Even the channel lengths are still the same. So think about what happened here before 22 or 24. What happened here? The idea is that if you have a shorter channel length, that means you get the current from this side to the other side faster. Because you get a channel shorter, you get a current flow within a shorter channel, you get a more higher response. And what happens here if you shorten the length? You shorten the entire distance between the substrate to shrink the device of your chip. Okay, you get two different benefits. The first benefit is the density can be down. So the only thing you need to deal with is how do we shift the dimension? Like you can develop a higher lithography critical dimension with better critical dimension, or you want to get a different from UV, DUV or EUV. So you can improve what is the wavelength, and then you can use better optical component, get a finer dimension. So that is a simple way. Once you shrink the dimension, you get a better performance because the channel length is shorter, you get higher response, you get a smaller capacitance. Okay, so let's people how people earn money in 2000 years. Okay, back to that end. But later on, they find a really tough one because we already reached the limit, physical limit. What is the basic limit? Once you further shrink it down, what we want to apply for MOSFET is simple. We want to control the current just as we say. If there is no gate voltage, there is nothing. Even we have the source drain biasing. But if you have a really short channel, what happens here there is, as we mentioned, even we just bias source and drain, maybe there's leaky current. Okay, they start to have some leaky current appearing in the transistor. But once you have leaky current, what happens there? You destroy the performance of your device. Okay, so that is the problem. So people think about it the way I think it started from sensor. So they use different methodology. They say, okay, so we can use like a 18 nanometer, but for that 18 nanometers, the physical length of your channel it should be still 24. But I can say it's 18 because the performance and density is going up. But I use different way in terms of shifting the dimension. Okay, so for instance, you can shift the dummy area or can combine all of the transistor all together. And I think that maybe I'm not sure how many people heard about CFET, maybe next generation transistor. The previous one we work with PFET and the MOSFET, NFET, we call the CMOS, we call the complementary MOSFET. And then here we have two different transistors separated with each other. So you double the area. So what do they consider CFET? What is CFET? We try to connect with both attack like a three-dimensional transistor. So you can shrink the area by L. Okay. So that is something people going, how do we shrink the density using different way, even for each device? The channel lengths are still the same. And how do we boost the performance? That is the important thing. By the way, before we go further, before we go more advanced part, we want to talk about what is the fundamental part back to 14 years ago. Okay. For the fundamental parts, we started with the channel length, as we previously mentioned, and always we want to do some dummy thing that called max. Okay. For the mathematical derivatives, let us consider what happened in all of this stuff. So let's begin with the channel. For these channels, we call the channel length as L. And what happens for this L is that once you have the positive voltage along the metal for this P-type substrate, what happens here is that we accumulate the multi carriers as the electron. But once you have this accumulation, before applying any biasing voltage along source and drain, what happens here is you have an equal charge along the surface, just like we talked about metal oxide semiconductor. We work as a capacitor, so the charge is equal. That means no matter charge distribution is the low source or drain side, they get a similar, they get a really similar charge density. But since we want to conduct the current, the currents will be, the potential will be applied. For instance, the drain side with higher voltage than source side. So under that scheme, what happens here is that you get different voltage along the semiconductor because we say, okay, so we get a doping along one side, but this potential will not go into an abrupt change in between, right? Because the potentials will continuously change along the same semiconductor without any maybe different material connection or different. Only we use here is doping. Okay, so the epsilon will be the same. If you get this voltage, that means you get higher voltage here than here, right? Because we apply positive voltage in potential. So how do we judge it? How do we judge the current? So we start with the charge because we talked about charge before. So how do we talk about charge? We talked about the voltage dependent capacitor, right? In the next slide, we talk about voltage dependent capacitor. What is the relationship between capacitance and charge? We get a charge, we get a charge over time, we get current, right? But how much charge change within time, we get current. So as long as we know the charge information, how long it change response to your voltage, we know the current, and then we can derive the current density or how much density current we have. So consider that we have some accumulation here before applying the drain to source voltage. But now we connect, for instance, we get a grounded and we get a certain VDS. We get a drain to source voltage difference. Okay. And another scheme, what happens here, you get a positive voltage. If you get a positive voltage, you get electric field from these waves, right? So if you get electric field from this wave, that means you get an additional, sorry. So you get a charge, because it is positive field. Okay. So for this positive field, you get more, like you build up an electric field from here from drain to source. That means you get a positive charge more, you get a positive charge here and negative charge here. So you get more negative charge in consider to the drain side. Okay, so we can think that if you try to draw a curve of the charge distribution, that will give you a field channel. That means you get more charge accumulating along the source side, but you get a least charge accumulating along the drain side. That is what happens. So it should be a voltage dependent charge distribution. And then next we consider how do we evaluate the current, and how do we evaluate accumulation of the charge. So you can consider the before we judge how much precise value, you can consider if you apply the VDS, there will be a ID from drain to source, okay? From drain to source. And the other last constant, when you have the ID, what is the relationship between the VDS and what we call the VGS? Okay, so we have the voltage, and then we saw that the current should be voltage dependent. So the first thing is that back to the previous slide, back to the previous lecture online, we get the accumulation charge, which is proportional to what? VGS minus your threshold voltage. What is the threshold voltage? 2πf plus your semiconductor voltage, the security voltage plus any charge trend along the outside. Right? We call it the VT. We call it the threshold. Okay. So you can see it's the charge, or we can say accumulating minority carrier. So it is minority carrier. Which is proportional to VGS minus VT. Okay, so when you apply the voltage here, you have the fan also including the fan voltage, right? Because we need to first heal the fan. If you get a different work function between metal and the semiconductor. Okay, so there will be some connection, the fan voltage plus the depletion voltage plus the total surface voltage. So other schemes, you have the charge, which is proportional to its current. And once you have more charge, that means you have higher current. So the current will be proportional to this one. Okay. And then the other thing is how the current related to the VDS. That will be simple because VDS is a forward balancing, just like in a conductor. What is the current versus your applied voltage? It should be just proportional to the applied voltage. Okay. So if you want to say, okay, so for ID, it will be proportional to VGS minus VT multiplied with VDS. That will be a simple way. Okay. For this time, I think before we do any calculation, we can consider on both sides how large the channel is and how much current we drive using external bias. Okay, so even within a simple conductor, I'm not sure how many work in transistor or making the full port system, but it doesn't matter. When you work with, I'm not sure you use your motor. If you drive higher voltage along the motor, you get higher current. It's rotated. It speed up, right? So that was something happened for this. Okay, and for this one, you just consider how much channel will accumulate here before it pinch off. So other schemes we consider, if you try to draw the figure on the different scheme, for instance, I want to show what is the relationship between ID, the major current along this way. That will be related to what is the VDS. Okay, so for VDS, that's simple. You just go up with higher voltage, just like a regular transmitted line. We get a higher voltage, we get a higher current. And how about the other way? How much channel we get? You get different channel, different slope. That means you get for instance, your VGS minus VT is either maybe 0.5 VGS minus VT, 0 VGS, maybe 0.2 minus VT. So different slope means you get a different channel accumulation. The higher voltage we use below the 258, we get a higher multi-carrier accumulate a queue along the semiconductor surface to get a bigger chance to conduct the current. Okay, so that is a general way. But at times it is give you a pinch off. So what does this mean? This means your voltage along drain is too high, and it will impact the performance of your accumulating channel. For instance, if you are working with VGS along 5 volt, for instance, you get a 5 volt. Before we apply any drain to source voltage, what is the voltage difference between source and gate? We call it gate. We get a 5 volt difference. So you can see, start back to the previous one, we bend down the larger accumulating. The Fermi level is the same. We bend down the intrinsic level. So the Fermi level is higher. Okay, so we bend down the curve for p-type system, right? We get positive voltage, we bend down the curve. We pivot, it is in below, the Fermi level is below intrinsic level, so it is p-type system. But later on, you bend down the intrinsic level, Fermi level is still flat, so Fermi level is higher than the intrinsic level. You get the accumulations of the electron along the surface. Okay, so for this bend down, what happened here is that, okay, so we get a sound accumulation, but if you apply the positive voltage here, like a 5 volt for instance, still the same with it. What is the voltage difference between semiconductor and metal? Nothing, right? Because you also apply the same bias voltage. So what we really consider, voltage is like a reference level. We only have a difference in between. There's no absolute value of voltage. Like say this pencil is 5 volt, this trunk is 5 volt. It's nonsense because always we need to have a ground voltage as a reference. So if you consider rising this VDS further, what happens is that you pinch it off because there's no channel, because there's no voltage difference. Okay, so other than the constant, what happens here is you get certain saturation. As long as you have the current, would that be possible to get nothing, no current there? It's not actually possible because always you get a certain flow along the carrier. Okay, so what happened here is that if you look at the trace of this curve, we should derive the information or equation similar to this proportional trace. Okay, so that's what we want to start with. Okay, and then next we want to start with the charge, how much charge we can go, and what is the practical way. So what happened here is that we use the proportional, like we proportional to VGS minus VT and the VGS. But then what happens here is we want to have a precise derivative or derive this equation. So we first started after with the Q. So what is the Q? We can consider that the charge will accumulate here along a certain dx. It is the Q. How much charge we get here is the Q. Okay. So for this one, we can start with this one. How much Q we have equals to the R side multiplied with the area. Okay. So what is the relation between for the Q over C? Right. So you get a C multiplied with V, the voltage difference. Okay. So the dq is related to what is the CR side multiplied with W. And also this dq is in electron because we talked about p-type substrate. So we get the negative side. And we get the CR side. You can consider it is R side. So the capacitance of R side, which is epsilon R side A over D. Okay, so we multiply with W dx and the voltage difference, which is VGS minus how much actual voltage seen here. So we can say here is Vx, which is dependency to the distance minus Vp. And the Vp is what we mentioned, the deplete voltage, including background voltage, deplete voltage, and the trapped voltage in the previous lecture. Okay, so let's take a 10 minutes break.